So we'll continue our lectures on agentic workflows. So far we looked at incorporating tools during the fine-tuning process, and then we talked about how to teach LLMs to use external APIs. And now we are looking at some important problems in AI agents, basically for automating complex tasks. So just a recap, last time we looked at prompting techniques that people use and agentic workflows that people use to automate complex tasks. And then we talked about how having reasoning along with actions can help you get better complex task solving accuracies. And then we also looked at how the model can use itself to provide feedback to iteratively improve its performance. And then we also looked at how when we combine React with an explicit evaluator and a model feedback technique along with a little bit of memory can help even get the performance higher, right? So I think we stopped at a point where we briefly touched upon memory, and then we mostly focused on how iteratively solving a given task helps improve the model, improve the task performance. In this lecture, we'll focus on two important problems. One is how do we do memory management in AI agents, right? So the biggest problem with agents now is that you very quickly run out of memory. For example, if you have tool calls where let's say the tool response is a sub view of a table, right? So then it sort of ends, if you call the API twice or thrice where the backend database is say logs of observability logs of some application that you have, then it will quickly fill up your context. And similarly, when you have a long a platform where you can converse multiple times, like ChatGPT, right? You have like hundreds of sessions in ChatGPT, and sometimes when you ask a question, you should be able to leverage whatever you had discussed with it, like say 2 weeks back or 20 months back or things like that, right? So we'll see how memory management in AI agents is being performed, what sort of tools are available to you that you can readily use when you build your own AI agents. And then we will also look at another important problem that's becoming more and more relevant now. Like in the recent 2 months, the number of papers that are coming in archive for this particular problem has increased quite a bit. And the problem here is that can you make a small language model, let's say an 8 billion, a 3 billion, or a 1 billion model, work as good as a proprietary model for the task that you have in your hand, right? So the issues could be because of cost, the issues could be because of latency, the issue could be because of hardware constraints you may have. So this is becoming a more and more relevant problem now, and the prime focus here seems to be RL, right? So we will look at one very interesting paper on how they tackle these problem of fine-tuning a small language model for the task at hand, right? And this task is agentic in nature, in the sense it's a complex task. In the previous lecture, part 2 of using external tool calls, we did see how to fine-tune using RL, but that was specific for use of tools, right? But as you know, agentic applications are slightly more general. You can have iterations, you can have different types of prompts, you can stitch them all together and create a very complex workflow. When you have such a workflow in hand, what type of assumptions should we make, what type of prerequisites should we have so that we can fine-tune a small language model successfully, right? So this is something that we'll go through. Now let's look at memory management in AI agents. So MemGPT was one of the first papers that talked about memory management in LLMs for agentic AI applications. So the motivation is very simple, is that LLMs have very limited context length. So now you can say that most models support 128k tokens of context. Shouldn't that be enough, right? So looks like for most real world applications that is not enough, right? For example, just use ChatGPT. You see how many interactions that you've had with ChatGPT in the past, right? So now if it has to leverage all the interactions that you've had with you, then do you think like 128 context length would be sufficient to hold them, right? Like just imagine doing 2 coding assignments with it. You will already exceed the amount of context length you have, right? So that is an issue. No matter how big the context window becomes, it is always fixed length and you will always have issues, right? The second problem is that when LLMs, or when people come up and say like, look, I've increased the context length of the recently released LLMs. Now it's as good as having 1 million context length. Now it's as good as having 10 million tokens of context length. So that does not necessarily mean that the task performance would remain stable, right? For example, let's say you're doing RAG, right? Now, in the very beginning, large context was considered to be 8K. 8K itself or 32K itself was considered to be a large context length, right? So now people had issues with RAG saying, look, my retriever is not that good. Now, if you increase the size of the context, maybe I can get better accuracy in RAG, right? So then people work with people expanded it to 64K, 128K. Now it's up to 1 million, right? So, the recent GPT models do support 128K context length, and for one such task of RAG, here you see that the more documents you retrieve, the performance does not remain constant, right? So ideally, what should happen? It should monotonically increase, right? Because the more context window you have, the likelihood of it containing the document that contains the answer is going to increase, right? But at the same time, the amount of distractors are also going to increase, right? So the performance is not going to be just because not going to improve just because a gold document is present in the context, right? And there was a recent paper in 2003 called "Lost in the Middle," which says that even position of where the gold document lies matters a lot, right? So if you take 20 documents, right, and you change the position where you keep the gold truth, then the performance of the model changes, right? So if it is in the first position, you get an accuracy of slightly above 75, but if it is in the 10th position, then you get an accuracy of only 55, less than 55, which is like 20-point drop in numbers, right? So just because you have infinite context length or very large context length doesn't mean that you can effectively leverage the entire context, right? So if you know that, look, I'm okay till 65, so I will support till the third document, there is no easy way wherein you can achieve good performance by fixing the context length, right? So some sort of memory management is needed to make sure that you keep the context length slightly smaller, but somehow provide it an ability to push the necessary documents there or change the context based on what needs to be done at this point in time, and that's what memory management is going to be here in this paper. So now the problem is, how do we provide the illusion of infinite context without loss of performance, right? And here there are different techniques people are taking. Like for example, for this long context thingy, they don't want the position to be biased, so there is a separate thread of work on how do we make LLMs invariant to position bias, right? But the other line of work is this memory based work, where how do we provide the illusion of like huge context length without dropping performance by use of memory management techniques, right? So MemGPT is inspired by the idea of virtual memory paging. So as you all know, in our computers, we do have RAM and disk, right? And let's say you're going to access a very, very large file, or the code base that you're going to run is extremely large, right? And the entire code base cannot fit into the memory. Then obviously, virtual memory management comes into play, right? So it only fetches some information, puts it in the memory, in the physical memory, then the program uses it, and once the program requires access to something that's outside the physical memory, there is a virtual memory management system that lies underneath, which will make sure that it uses some technique to swap a not so frequently used page into something that is necessary at the moment from the disk, right? So MemGPT is inspired by similar virtual memory management technique, and they call it virtual context management. So basically the LLM's context is fixed, right? 128K or slightly less than that, and you equate that to the physical memory or the RAM that you have, and you use some sort of an external storage, let's say a Cassandra DB or something like that, which has access to almost infinite amount of memory, and it's analogous to the disk. And what they say is the communication between the LLM context and the external storage comes through by defining some sort of tools that you have and using the tool calling ability of LLMs, right? So what are these actions that this memory management system can perform, right? So some of the actions are, it can read or write from an external data source, or it can read or write from some part of the internal context as well, right? And it also decides when I should do memory operations and then when I should call back to the user, right? So this is a very generic architecture. If you want to work on an agent and then you feel like context management becomes a big problem, then you could draw lessons from this particular work and include that. Now they also have some sort of prompts and ready to use resources available which you can use and then plug in your agent design into it, right? So let's see how it looks like. So they are logically dividing the context into three parts, right? One part is called the system instructions. So this is a read-only part. You cannot write to it, and what it typically contains is the instructions for the agent that you have. Let's say that you're building a RAG agent, then it would have instructions about what you want the RAG agent to do, and it will also have descriptions for the MemGPT OS, right? So by that what I mean is, like, it will define, like, look, I have a context, I have these parts in my memory, and then I'm allowed to do these operations. This operation will take these as the arguments, and then they will take data from this component and move it to this component, right? So they will describe the entire the virtual context management process they have as system instructions and make it available for the LLM. So that will consume a good chunk of space. The second thing is called a working context. So this working context allows both read and write, but this is writable only by the MemGPT tools and not by the user or tools executions and things like that. This is only a scratch pad for the MemGPT operating system. And why do we need working context? Working context will ensure that long conversations are consistent. Like, you might have come across this concept of memory even in ChatGPT, right? So sometimes when you talk, it updates. There is a small sort of pop-up that comes in the bottom that says, like, memory updated, right? So when you're conversing with the user and when it feels like there are some personalized information that's very specific to you that could be reused or leveraged at a later point in the conversation, then it will typically write it to the memory, right? For example, if you say that I have difficulty in the course that I'm taking, and you describe the course, then it will probably want to save that information, saying that this person is taking this course. Maybe later on when they ask some ambiguous question, I could make use of this particular information. Or you say that you're studying at IIT Delhi, right? So then it will save that information and say later when you say that I have an issue with this policy in my institute, so then you can, like, co-reference the actual institute that you're in there and then search accordingly for it, right? Yeah, so I will get to that part. So that information is typically written in the working context. Let's see how this working context is anyway available during the response generation, which is the output buffer, right? So this will be leveraged. So you will have to define rules for what you need to save, and it will leverage whenever it needs it. So for example, here it says that how was your day today? And the other issue with other reason why we need working context is that sometimes when your conversation gets too long, right? So then you need to save some important information from the ongoing conversation with the working context so that you don't lose whatever you've discussed in the past as well. Like, for example, here it says that how was your day today? I had fun with my boyfriend James, baked me a nice birthday cake, and then and it says happy birthday. And now there is an alert that goes to the system saying that your context window is almost full. So now when it has to purge some of the old utterances, it's good that it remember certain things. Like here it knows that February 7th is the birthday, he's a birthday, and the boyfriend's name is James, right? So this will go back to the working context, and you can purge some of the message history, right? So this is where the working context stores some important information about the ongoing conversation or anything else that is like used as a scratch pad by the MemGPT OS. And finally is the FIFO queue. You can consider this as a rolling history of the messages that have been going so far. So and the pink part here is a summary of whatever conversation that has happened so far. So if you exceed the FIFO queue size, then it will do some sort of a recursive summarization where it will take the summary, take the messages it wants to evict from the FIFO queue, and it will create a updated summary and puts it back so that the FIFO queue gets empty. right? So these are the three parts in the input. You have system instructions, you have a working context, and you have a message history, right? So ideally we would assume like everything would be system instructions and message history, right? And when you run out of space, the most likely thing you would do is remove some part of the FIFO queue and then end up using it. So this is slightly more sophisticated than that. Now in addition to this, they have two important memory. One is a recall storage and other is the archival storage. So let's first focus on recall storage. So recall storage is basically is a database of all the messages you've had so far. So if you take ChatGPT as an example, all the conversations, all the sessions that you've had so far will be in the recall storage. Yeah, so the queue manager does most of the work in managing the FIFO queue, right? So whatever logic that you want to write for how this summary should be recursively done, and how to save messages, what to when to call the so it also its policy is also it should also enforce the eviction policy, which is like iteratively summarizing and then removing some messages, one such policy. But you can write whatever policy that you want, right? And it's many a times also sends a warning message saying that you're about to exceed memory, so that the MemGPT instructions has some information about when such an alert message is given to you, then you can write whatever you want to the working context so that you don't depend fully on the queue manager to summarize, because a queue manager can summarize it in a different way, right? It may or may not be task dependent. So it typically sends a alert so that in case the MemGPT wants to update its working context, it could do so. And finally, archival storage is more like it's not just chat history. You can store a lot of additional things as well. Like for example, you can store like a lot of conversations from different users as well in your design, right? For example, you may want to not repeat the same mistakes you did in the past with other users, right? So you know that you took a certain path, it didn't turn out to be right, and you want to go back to a different path. So if you have made those mistakes in the past, you could use that learning and then probably update your working context or use them as in-context examples to make sure that these issues don't happen. So you could use some things like that, or in case of RAG systems, you could store a lot of documents here and then say that, look, I have this information in my archival storage, and use it whenever you feel is appropriate, right? So so this is the sort of setup they have. In addition to the system prompt, they also provide a set of tools for MemGPT to use, and these are some of the tools. Send messages. You at this point in time you want to send a message back to the user, and then working context append is like you have the working context that I showed in the middle, and you can say that add this to my working context. You can say replace, and if you replace with an empty string, then it will remove that particular information from your working context. And similarly, you have operations for the recall part as well, where you search your message history to find something relevant. You can also use archival memory, and archival memory is typically read-only, or you can also have some things to mostly read-only, but sometimes you will also enable it to write as well, so you can use memory insert as well. So there are two types of experiments they do in two different setups. One setup is MemGPT for conversational agent. This is more like ChatGPT, right? So what is more important here is how do we make use of the recall memory and the working memory, right? That is a crux for this experiment. So they want to measure two things. One thing is consistency. If you've already talked about your birthday, you should not be asking the user back. If the user in the past has said they prefer dogs over cats, now you can't the conversation you have going forward should be consistent. If they want some suggestions for their pet's birthday or something like that, then you should know that since they have preferred dogs, it's very likely for them to have dogs, and then suggest accordingly, right? So you have to have a consistent agent that makes use of all the conversation history that you have. Second thing is engaging. So when you start talking to people, typically when you ask them very like usual questions like, oh, how was your day? How was the weather? Is everybody good at home? Then it doesn't look very engaging and personalized, right? It feels like they're just asking for the sake of asking you. But let's say if they say, hey, how is your friend? And then say your friend's name. And then you said, last time when I met you, you mentioned this. How did it go? Right? So when you have a very personalized way of interacting with the user, when you meet them after a break, then it sort of helps you engage a lot better, right? So engagement is also one aspect that they want a good conversational agent to have, right? And so we will look at one set of experiments on that, and the second set of experiments is on document analysis, basically like archival memory. Like if you have a lot of documents in the corpus, and let's say you're doing something like a RAG setup, how effectively can it leverage the archival memory without you having to handhold it? So for the first task, with this MemGPT for conversational agents, they use this data set called multi-session chat, right? And the way this data set was constructed is humans were given a certain personas. Okay, let's say that there are two humans. Each were given their personas. So for example, persona for a person A would be, I'm married to my wife and I have 2 kids. I haven't been to Disneyland. I love going to concerts and things like that, right? And similarly, persona B says that I'm close with my family. I have been to Disneyland. I love Mickey Mouse. I work as a baby delivery nurse. I like to learn to coupon to save money, and I applied for scholarships, right? So now when these two people have conversations, then the conversations would look like this. Hello, how are you doing? And then B says, I love spending time with my family. That's great. Me too. I'm married and my husband and I have 2 children, right? It goes like this. So this is consistent with their personas, right? And the way they've, so this is one chat session. Typically one chat session has around like 12 to 15 messages. But in addition, and then there is, they simulate a time gap. And then they have multiple sessions. So each multi-chat session has a total of 5 different sessions in them. So this is how the multi-chat setup looks like. And to test their consistency experiment, what they did was, after the 5 sessions, they asked LLM to generate a follow-up question which would leverage some information from the conversation so far, right? For example, one such example is like, hey, remember the time we talked about music? What was the artist you mentioned you could get into? So this sort of refers back to the conversation they had, and here the answer should be Taylor Swift, because that's the only musician, the artist that was referred in the entire 5-session chat, right? So a good system with a system with good memory management should be able to recollect to make sure that that conversation is consistent, right? And it not necessarily have to be like one entity. Sometimes it can be a slightly more elaborate answer, like I eat a fresh and raw diet to save on groceries, right? Things like that. And this will be well aligned to the persona, right? As well. So now what they say is that when they ran this experiment with all the generated data set for consistency, they used two evaluations. One is called Rouge L recall. This is more a lexical similarity based metric, where it sees whether the word overlap between the generated response and the ground truth is good or not. And they use recall because most LLMs tend to generate quite a long answer. They won't just say Taylor Swift, they'll say, oh, I remember you saying Taylor Swift and blah, 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 right? So they use recall because recall computes whether the ground truth is present in the answer or not, rather than penalizing the model for generating extra, right? And accuracy is LLM as a judge. It uses GPT-4 to evaluate whether the answer was present in the prediction or not, right? So what they say is that GPT 3.5 and GPT-4 Turbo, if you use them out of the box, they simulate a scenario where you cannot fit all the multi-chat sessions into the memory. So they do some sort of a summarization and put them back into the context, right? So when you use that, the accuracy seems to hover around 30 to 40, right? This is LLM as a judge. But when you give it access to MemGPT in the current setup and put all the messages into the recall storage, right? So then the model is able to figure out how to use it. And by doing so, it is able to achieve like quite a big improvement compared to using a summarized version of the chats in the context window, right? Any questions? Okay. So you might see that there is quite a big difference between using MemGPT with 3 series models and 4 series models, right? 3 series is still at 66.9, but 4 series is at 92, 93. So the issue here is like 3.5 models are not good at tool calling, right? So even though they have those tools that it can access, but it's not able to make the right choice on when to use what tools, and that's the main reason why it's not doing good. But GPT-4 series models have very good ability to do tool call and figure out the right arguments and when to call what tools and stuff. Similarly, for engagement, what they say is that let's say that you already have 2 sessions or 3 sessions. Now, 4th session, how would you initiate? Right? So that the more engaging it is, the better it is. Right? So what they did was they asked humans to write a a sort of conversation starter after that many sessions, and they also have access to personas. Right? You already have personas, right? So let's say that you have personas of A, personas of B until like session 3, right? So then whatever in starter that like the other user creates should contain a lot of information from the persona that you have, right? So similarity 1 says that so there are a lot of facts in your personas, whichever fact has the highest similarity, you take that, and that's called sim1. So you will have, like, say 20 facts in persona A. You generated some first from utterance to engage the user, and what is you compute similarity across all of them and take the max, right? That's sim1. Sim3 is you take the top 3 and average them, right? So this will say that how many you can talk about a lot of things, so that you will pull the user at least in one of those things, right? So you see both sim1 and sim3 are quite high. In fact, it is better than humans for GPT 3.5, 4 and 4 turbo, right? So, and sim-h is similarity with respect to the human, of course. So that's why for human it's 1, for the remaining it's around 80. So engagement is also good. So finally, they want to study how it ends up using archival storage, and so for that they use something called natural questions. It's a data set that's grounded on Wikipedia. It has questions of this type: who was the ruler of England in 1616? What is the hot coffee mod in San Andreas? And all these informations are present in Wikipedia. So they have Wikipedia pages available in the archival store, and then they see how it affects the performance. So basically, MemGPT has this ability where if you're searching your archival storage, you cannot get all the search results. Okay, when you don't give the page, it will give you the top 10. Okay, when you say page 2, then it will give you 11 to 20. Okay, so now let's say if the first output is archival storage search Nobel physics for this question, who won the first Nobel Prize in physics, right? So then it will look through all the 10 documents, and then it also would say like showing 10 of 124 documents, page 1 out of 13, just to give some context to the LLM. So now after reading this, the LLM can decide based on the MemGPT instructions that should it answer now or should it go for the next page, right? So this will because you can only fit 10 documents in your memory that you have, right, in the FIFO queue, because the output of this will be fed back into the messages, because this is a tool message. It will be fed back and into the FIFO queue. So then it could do that. Now let's say that it's a multi-hop question, like we saw in hotpot QA and things like that. So then it may write something to the working memory as well and keep it there, so that it will form the second question later on, right? So these are all what is available to the model. You don't have to explicitly teach it. Most of it is already in the MemGPT instructions, right? So now they compare across baselines, which is if you retrieve top K documents and feed it to GPT 3.5 or 4 or 4 or 4.0, 4 turbo, then how does they perform, right? So you see for MemGPT, it is fixed because there is no restriction on number of documents, because the archival storage search system lets you to scroll through the pages and then decide what is to be done. So it's constant. Again, the difference between 4 turbo and 3 is that bad ability, not so great tool calling ability of 3.5, and that's why MemGPT with 3.5 is a lot lower, right? And MemGPT with 4 is much higher, and the same issue exists, right? The more and more you increase the context window, you get more distractions, and the model does not generalize well. So just because GPT-4 supports a higher context length does not mean that the performance is going to improve. In fact, if you see, if it had only used one document, it's getting 40% accuracy. But if you allow it to use 200 documents, then it's much worse than just using one document, which is counterintuitive, right? So like this is not effective use of context length. So what MemGPT says is that even in case where the context length is high, it can still do an effective job in the final task performance, right? So memory, so yeah. So now we've covered the paper called MemGPT that does memory management in AI agents. Of course, after MemGPT, there are a lot of other works as well. In fact, the MemGPT folks also made a startup out of this effort called Leta AI, which sort of is an extension to this, which supports LangChain and other platforms where you can easily plug in the memory management into your agentic application, right? So now let's go to the second part, which is how can a small-sized LLM approach proprietary models? So here the cap is not because of tool calling, but the paper says that the cap is because the retriever sucks, right? So the retriever is not able to retrieve the relevant document at all after those many pages as well, right? So that is the biggest issue. So if you have to fix anything in this particular setup, and if you have to improve it further, then you should improve your retriever. Okay, so for this particular work, we are going to look at a paper that introduces a benchmark for this particular task and also creates a novel algorithm for it, right? So in two classes before, we discussed a paper called Magnet that does fine-tuning for multi-turn tool calling, right? And there we discussed multi-turn DPO as one possible approach that you can do, where if in addition to positive trajectories, if you have negative trajectories as well, then you can use it in the DPO loss and then better learn tool calling to avoid the pitfalls that you typically go through. So that is, so you know there exists a work, right? Now these guys, what they're doing is that sweet RL is considered would do better under certain circumstances, right? And we'll talk about what those circumstances are and how it gets better, right? So before that, we'll talk about a new benchmark that these guys released called collaborative benchmark or call bench, right? So this is a benchmark where an LLM interacts with a human over multiple turns. Like let's say if you take SweBench, right? SweBench mostly consists of the first issue and access to the code base. But let's say if the model decides to interact with the user, that typically happens, right? Somebody raises an issue on GitHub, and as a developer, you don't understand what it means, or you need more information, right? So you don't directly jump into solution. You try to figure out all the additional information to reproduce the test and things like that. Maybe sometimes when you try to reproduce the test, you're not getting the same issue as what the user reported. So you understand their context, you understand their platform that they're working in, which library version they're using, things like that. So SweBench is not that great in multi-turn user interaction. Similarly, we discussed TauBench, if you remember. So TauBench, you are given a user task at hand, and you also have a user simulator. So when an agent gets back to you, the simulator will respond back with some additional information that is needed, right? So similarly, in this setup, they collected multi-turn conversations between human and agent for achieving a particular task. And these tasks are programming and front-end web page design. These are two tasks that they take, and they propose a new RL algorithm called Sweet RL, which is RL with stepwise evaluation for training time information. So the main difference here is that in addition to the positive and the negative trajectory, you also have some additional information that is available only during train. For example, in programming cases, you may have unit test cases, right? Only for the training data, not for the test data, or during inference you might not need unit tests, but you can use some signals from some additional information that is available to you during train. So which means like you can use Sweet RL only if you know that there exists some additional training time information, right? In case of Magnet, we synthetically simulated negative trajectories by replacing the right tool call with incorrect tool call in between the trajectories and call it negative, right? But in this particular case, in addition to having negative trajectories, you should also have some sort of additional training time information. That's like the biggest assumption that they make here. And they follow an actor-critic model where the critic will look at whatever you've done so far. It will look at the training time, additional information it has, and decides whether you're going in the right direction or not. So you have a critic model. You have a separate critic model which will look at whatever you've done so far, what action you just took, and it will give the reward by looking at what eventually you want to do, by looking at the unit tests and things like that. And that information is fed back into the RL algorithm for optimizing the policy, right? So now let's look at call bench. Call bench, like I said, has two tasks. One is the backend programming. So here the agent is required to collaborate with human simulator to write a Python function. So what is provided first is that with a very high level description of what is needed without dwelling into a lot of detail. So they deliberately make it underspecified, right? So you tell what you want, but you don't tell the full details of what is needed, and you also give some function head signature, which is name of the function, what arguments it takes as input, right? Now it's the job of the agent to interact with the user and then collect as much information as possible and then write the final code, right? That's the task at hand. So here the user is given, the user simulator will have access to the entire code, the final output, right? So that when the agent asks the question, you can look at the code and then answer back saying, oh, this is what I want, this is what I should do, and things like that, right? So this is the task, and the data set is that they have Python functions and their high-level descriptions and unit test cases generated by Llama 3.1. So it contains the entire Python function that you want the agent to finally come up with. It has a high-level description of what problem you're trying to solve and what the function signature should be. And what they did is they executed the Python functions on the unit tests, and if all the unit tests pass, they keep them. If any of the unit tests fails, then they throw away that particular data point. By doing so, they generated 10K training tasks and 1K test task, right? So now you have the task at hand. You have the Python code, you have the first utterance, you have the unit test. Now what they did was they gave the initial utterance. They have a user simulator at hand, right? So the user simulator gets access to the entire Python code. So what they did is they used Llama 3.1 8 billion model, which is a small language model, as the agent, right? So and the human simulator is done by 3.1 70 billion, slightly bigger model, right? So now after you give the first user utterance, then the 8 billion model will try to solve it, right? It will ask for some information back. So now the 70 billion model has access to the code. It will look at the code and then it will respond back to the agent, and it keeps on going. And they have a certain limit of, I think, 10 or 15 turns, and if it doesn't solve, then they will consider it to be done, right? And now with that, they generated 15K trajectories, right? So now there is a certain instruction in the model that says that if you use certain phrase, then I would consider everything following that as the code that I should execute. It's in the instruction, right? So let's look at an example. So this is the code snippet called recognize tribe, which takes ancestral data and demographic stats as input, and this is given to the user simulator, right? And then the first utterance is, I need a Python function that determines whether the government should grant recognition to a tribe based on their ancestral and demographic data, and that's it. So it doesn't give any information about how you should do that, right? So now the Llama 8 billion model will come back and say, to provide helpful functions, can you please clarify what specific information is contained in ancestral data and demographic stats arguments? For example, what kind of ancestral data is it? Example, percentage of indigenous population, historical records, tribe timeline. So it will ask this, and now to answer this, the user agent will have access to the code. So it will look at the code base and it will answer back, right? So this back and forth will keep going until the model says, I want to answer : and gives the Python code, right? So now you have access to the unit test. You can execute the Python code and say whether this succeeded or did not succeed, right? So you will have, with 10K tasks, they were able to generate 15K trajectories. Some of them would be positive, some of them would be negative, right? Now, if you look at, so you can force or write your prompt in such a way that you force the model to answer right, to generate the program right after the first user utterance, right? Or you can let it go back and forth with the user simulator, and then when you feel it's the right time to generate the code, you can generate the code, right? So why are we doing these two setups? These two setups will help us understand whether you need to collaborate with the human or not, whether the data set is rich enough that will benefit from the collaboration, right? So it's very clear from the, percentage of test passed is, you have 10 tests associated with each code task, right? What percentage of them got evaluated in average? And success rate is all 10 should succeed. What percentage of tasks for which all 10 succeeded in the test set? And you can clearly see that if you don't collaborate and you try to answer it in just a single turn, then you get around 20s. and between 20s and 30s, and even GPT-4o is not able to do a good job, right? Because of course, if it's underspecified, like how can it do a good job, right? So, and of course, after you allow it to do multi-turn, then it's able to achieve somewhere close to 40% success rate or 54% test pass rate, right? Which is like twice or thrice of what you would achieve in just single turn, which shows that this benchmark is actually in fact collaborative in nature, right? They also have another task called front-end design collaboration, where the user has a web page idea in their mind, okay, and now they're trying to convey it to the bot and ask it to generate code for the HTML. That's the task at hand, right? Of course, same as before, in the first user utterance will always be underspecified. It will abstractly say what needs to be achieved without dwelling into a lot of details, but it will deliberately mask information like layout, what color palette, and things like that. And so you have to interact with the user simulator. The user simulator has access to the web page so that it can respond back to the agent, right? Now again, same as before, they use a data set called website, which has reference web pages and high-level descriptions of those reference web pages. And they have 10K tasks for training and 500 for test. And similarly, they generated only 6K offline trajectories from the 10K examples. I'm not sure why it's only 6K, whereas previously they generated 15K from 10K. And maybe they ran into some issues and things like that. So same as before, they use a agent which is small language model, but here since they also use the image of the web page as an input rather than using a language model, they used a vision model. So they use Qwen2 VL 72 billion model as the human simulator, because it has access to the rendering of the web page as an image, and then it acts as a simulator. Again, same as before, it may have positive trajectories or negative trajectories as well, all the 6K. So this is how an example looks like. This is the image in mind of the human who is interacting with the bot, and they just say that I want to create creative agency, a playful and visually stimulating design with a diagonal grid pattern, a logo in the top left corner, and a call to action button predominantly displayed, bright and bold color palette, right? So they deliberately made it very vague. And so again, the system here comes up with a web page design, but also poses a bunch of questions where it has made assumptions and things like that. And then same as before, the user keeps interacting with it, and at some point in time, the model would say that render.html and gives the right one, right? And when it stops here, what they do is they compute an image similarity between what the agent generated and what the ground truth was, right? And here the image similarity is around 88%, which is pretty good, right? So these are the two data sets we have, and same as before, here it also shows average cosine similarity and win rate. Win rate here is with respect to they showed the output of GPT-4o and the current model at hand, and they wanted to see GPT-4o did better or this model did better. And of course, so GPT-4o is at 50% win rate because of that, and collaborative GPT-4o is used as the other model. And then same as before, even though the cosine similarities are pretty close, not that far away, maybe 10 points at max, the win rate clearly shows that even for a 70 billion model as well, it is 3 times better if you collaborate on what is needed. Now let's move on to how does the small language model does. So we know that we want to look at collaborative setting, and we know that GPT-4o in a collaborative setting is getting 40% success rate for backend programming and 50% win rate in front-end design, right? Now if you have, let's see, now they want to see how does 3.18 billion instruct out of the box performs, right? So clearly there's a big gap. The success rate is 22, which is almost as half as what GPT-4o does, and its win rate is 33 at the moment, and we want it to be as close as 50, right? Now, now you have successful trajectories and failure trajectories that you've generated for both tasks. Now, given that you have this data, how would you fine tune Llama 3.18 billion instruct?
We have to try to pass, right? So
correct.
If we have 10 units and it's only passing the two and failing the rest, we can say, okay, your code is failing these units and keep on repeating that.
Okay, so you're saying a way to improve, right? So let's say you're heading in the right direction. You want to use the clues that are coming from the unit test. So you in the 15K trajectories or the 6K trajectories you have, you know what all examples passed all the unit test. So they should be right. So you have a trajectory of how an ideal interaction should be. You may not have 110K test cases. All of them may not be true, right? But you have a subset. So could you use that to make the 3.1 model better? Can we fine tune with that data to make 3.1 better? There's a series of interaction, right? You can give whatever has happened so far and predict the next utterance. So when you have trajectories like that, and then you ignore the negative trajectories and only use the positive trajectories, that's called rejection fine tuning, right? So simply, does that make sense? No?
So we are training for the correct trajectories.
Correct. So which eventually gave out, which passed all the unit tests, or cases where it was better than GPT-4o, something like that, right? But if you use all data, then you will be teaching it to do wrong things as well. So we don't want it to teach it wrong things where it has failed. So you use only the ones where all the unit tests pass or it's better than GPT-4o. And if you do that, there is obviously some increase in performance, right? So you're showing it some right directions, but you're not using the negative examples here, right? Only positive examples. This is called rejection fine tuning. Still, there is a 6-point jump in success rate, but still there is a gap to what you can achieve with GPT-4o, right? Now, what would be the next step you would do?
Align it away from the wrong.
Correct. Absolutely. And like when we did magnet, we saw one such technique, right? Which is we can use alignment techniques like DPO and specifically multi-turn DPO. You have the entire positive trajectory, you have the entire negative trajectory. So there is we saw that there is a modified version of DPO called multi-turn DPO, where rather than using just one action, you go over the entire trajectory for all the loser all the winning trajectory, and then you use that in your alignment to make sure that you learn from the negative examples as well, right? So the only constraint is that these are for the same task. You start off with the same task. Maybe in one case you went into the negative thing, and in one case you went into the positive thing. So you show both and let the model decide, align itself more towards the positive and also learn from the negatives as well, right? So this is the multi-turn DPO. So of course, now the difference between rejection fine tuning and multi-turn DPO is that rejection fine tuning only use positive trajectories. Multi-turn DPO use the negative trajectories as well, with which you see 6 more point jump in success rate, right? But we are still slightly behind what we could achieve with GPT-4o, right? So this is where Sweet RL comes into picture, right? So let's see what it does. Now, before we go into Sweet RL, let's see what is that issue in multi-turn DPO that you should address to bridge the gap, right? So one issue typically in RL is called credit assignment issue, right? You have an entire trajectory. Let's say that you did 10 turns between the agent and the user, right? Now you're saying this trajectory is bad compared to the other trajectory, but you're not saying because of which step, because there are 10 agent utterances. It might have gone wrong at any of those. On an average, saying everything is wrong may also be bad, right? Because until some point in time, it might have done good, right? After which, or it may so happen it made a mistake at some point in time. After that, it did a good job. So penalizing everything is an issue, right? So the more pinpoint you say where the issue is, then you do better credit assignment, and that may lead to a better training algorithm, right? The trajectories are the same. You still have the same negative trajectory, you still have the same positive trajectory, but you just have to figure out how to give more precise feedback to your training algorithm so that you can leverage it, right? So here in the past, right, when we created the positive and the negative trajectory, we know everything is right. The negative trajectory, when we created for magnet, we deliberately changed one right function call with an incorrect function call and let the model flow from there. So we know for sure where we made the choice to make it wrong, right? But we don't use that information in the training, right? Even though that's available to us during the training, right? So what they say is like, there are certain conditions or certain cases where you are able to pinpoint, then we can use you can use our training algorithm to make it better, right? And the condition that they say is that you need access to additional training time information, and by that they say for back end task, you tell me whether this trajectory, like give me access to all the test cases. Like I want to see all the test cases, so I know this is the test case that I'm heading towards. Or in case of front end, they want access to the web page of what it should look like. So what this helps is that even though the information is under specified, it will look at the test cases, and the test cases, it will know that, oh, they're asking for this test case as well, so this might be a corner case, so maybe I should ask for some more information to make it better, right? It just needs the test case. It doesn't need the execution of the test case, because if you're in the middle of the conversation, you cannot execute the test cases, right? So what they're saying is just the presence of that test cases that you're going to test with will help me decide whether I'm going in the right direction or not. Similarly, if you just give me the image of the web page, I can figure out whether I'm going in the right direction or not, right? So, so the critic, what the critic will take is the conversation that has been going on so far, along with the additional training time information that you have. This critics, that additional information is not needed during inference, it's only needed during the train, right? And with that information, they will train a critic model, and the critic model will act as a reward function. And the reward function will go back to your policy improvement. And once you learn the policy, you can throw away with the critic. You don't need the critic anymore once you have the policy. Then during inference, you can just give the whatever conversation history, and it will be able to predict the right next action, right? So there's a two-step process. In the previous approach, if you remember, it's just a single step process. There's no critic. Just give positive, negative. The equation implicitly computes reward and then assigns it, right? So this is an explicit actor critic model where you first have to train a critic model which uses the additional training time information, and then you will train your policy, and after training you can throw away your critic and keep only your actor. Okay. So this is a more formal definition of what this POMDP setup looks like. And in POMDP, your environment is not fully observable. So in this example, the user's mind has the web page in them, but they will express it only with the text, and the text is not complete, right? So the part that is visible to the agent is called observable part of the state space, which is whatever the user says in natural language, and the program they have in mind and the image they have in mind is hidden from the agent. Agent doesn't know, but it is there in the environment, right? So those are the O and C. O is the observable part, the state space that is observable, and C is the state space that is hidden, right? So O1, which is a sample point from the state space, is the first utterance that the user will provide to the agent to solve the task, right? And OT is like all the interaction history until that point in time, because the entire interaction history is visible to the agent, right? And the hidden part of the state is the small c, which is a sample from the state space capital C. And for test case, for back end programming, it's the test cases, and for the front end design, it is the reference web page of the specification. And the agent action is a natural language, which is either the entire HTML web page generated one token at a time in the current utterance, or the natural language communication that it does to get more information, or it could be the entire the I want to answer and then the code. Like it can be anything. It's just a series of tokens with L tokens, right? At any point, any time t. So what we need to do is we want to compute a stepwise reward, which is different from the MDPO. MDPO, there is no stepwise reward. You have trajectory that is right and wrong. Here we want to compute a stepwise reward where I will give you the hidden information that I'm going to use during train, C part. I will give you the entire conversation history, OT, and the current action that I've taken. And you tell me on a scale of so and so how good or bad my current action is, right? Given the current state. Now, what we want to maximize is a cumulative reward. If you're going to interact for n turns, then I want to maximize the cumulative reward. This is what we want to do. Now we'll see how we end up computing the scalar reward, because that's the most important part, right? And that's where the critic model comes into picture. So I will not go deep into RL, but I'll just say that there is a definition for Q function and value function in RL. Q function is that given a policy pi, which is like the current model that you're fine tuning, right? So llama 3, if you start off with, then llama 3.1 is your policy. Given the current policy, then if you start, if you are at a state OT, which is current conversation history, and you've taken an action AT, it generated some output saying like, I want this information from you, right? What is the cumulative reward associated here? So from here, if I go anywhere, what is my expected reward, right? You are in the state and you've taken this action. What is the expected reward? That's what is computed. So from the time t till the maximum allowed turns, what is the expected value of reward that you would get on an average? And the value function basically tells you if I'm in the current state, let's say you're not taken any action. If I'm in the current state, then what is the expected reward I'll get for different actions that I take? Right? So a lot of actions you can take, and it will give you an expected value there. It is the expected Q value under the policy. So the policy will have an action distribution, that it won't take all the actions with the same probability. It will have higher probability with some actions and lower probability with some actions. So what is the expected value, that Q value that I will get for this particular policy's action distribution? And they also define something called an advantage function that measures how much is a specific action AT better than other actions. That's so if you you can easily derive this. It will just come out to be the difference between the Q value with OT and AT subtracted from the value function OT comma C. Okay, so you take this for granted at the moment, that the advantage function is a difference between this and what you should sort of understand is that if you give me the current trajectory, the action that the model said that it should take, and some information at train time, I should be able to derive something that's meaningful for you, right? And that's this, right? So for now, you take, like, if you give these three data points, it should be able to provide some reward that is meaningful. Now, how do we compute that meaningful reward, right? So in your hand, let's say that you started off from the same task, and one trajectory led to positive, where all the unit test cases passed, and one trajectory led to negative where at least one failed, right? So now this is the usual MDPO setup, right? It's a Bradley-Terry model, and what you're saying is that the only difference is like you are replacing all this particular setup with a reward function, right? And it also has the additional training time information C, right? OT plus is the positive trajectories, state and action, and this is iterated over all the times, every step in the trajectory, and same for the negative. What they say is that this reward, there is a proof in the paper that says this reward is equal to the advantage function that we saw in the previous step. And now they also show that this advantage function is nothing but whatever model that you're going to use for training your critic, right? So that is pi theta, and where it started from is the pi reference. And if you try to minimize this objective, then you would be able to, like, sorry, this is not the objective. The objective is this, right? So if you use this, as your objective, and you substitute a theta with this value, right? You have the positive trajectories, you have negative trajectories, then you will be able to train your pi theta model, right? And once you train your pi theta model, then you will be able to predict this value, right? Because this value is dependent on pi theta. So you use this objective to fine tune where only pi theta is what you're allowed to train, and you have the positive and negative trajectories, and as a result of that you will be able to evaluate a theta as well individually without positive or negative trajectories, right? So the goal of this is to finally come up with a reward function which you can provide stepwise reward, right? So this reward function A0, which will use the LLM that you're training for critic, and you run this, get this value and get the reference value, and then you average it over the total number of tokens you have, and it will be able to give you a reward for each step, right? So the biggest difference between this model and MDPO is that now you have a stepwise, you have some way to compute stepwise reward. So the crux is that if I ask certain questions and that is leading towards getting me a corner case in the unit test, then I'm going in the right direction. So during training you can use this, during inference you can throw away the critic model. Now you have this particular stepwise reward function trained using the positive and the negative trajectories that you have, and now we'll see how you can fine tune the LLM given that you have this reward function, and that is very straightforward, which is you take any task at hand, okay, and at any turn t, right, you generate multiple samples. You don't need positive negative trajectories anymore. You have the reward function computation thing, right? So you can keep OT the same until certain point in time, and then you sample 16 different actions, right? And then what they say is for all these 16 different candidate actions, you compute the advantage, because you have a network, critic network now, that if you give OT, AT and the true information C, it will be able to compute a reward for you, right? Once you have the reward, then you sample one from the top 50 percentile and choose it to be the positive or the positive trajectory or the positive action, and you choose one from the negative, choose it as rejected, and then you do DPO, like usual DPO. It's not necessarily DPO, you can use any algorithm there, right? If you have something that's better than DPO, you can use that. You can use PPO, you can use any such algorithm. So the good point is, like, they've trained an explicit reward model. Now you can do whatever you want with it, right? So now we've seen two approaches, right? One is the MDPO, which was used in Magnet, and now we have SweetRL. So can you summarize? So with respect to additional information, what are the main differences?
SweetRL, we have predicted scores each step and its future reward. And using that reward, we see if taking that step is advantageous to us.
Correct.
And then we take the two actions, one's positive and one is negative. And using those, we train the model as DPO.
Perfect.
Whereas in MDPO, we didn't score each step.
Correct. Perfect. That's precisely the difference. So MDPO assumes they don't need access to training time, additional training time information. SweetRL assumes that it has access to training time information. So you may apply MDPO for a lot more types of tasks, but SweetRL could be only applied to certain tasks where additional training time information is present that can give you the right clues, right? And of course, like you clearly said, this does it stepwise, whereas MDPO does not do good credit assignment. It generally tells you this trajectory is better. I don't know which one of them is incorrect, but the turn level credit assignment is much better in SweetRL. We cannot claim that it is perfect, but it's much better than DPO, right? So now we can see that the Llama 3.18 billion trained using SweetRL, which has a critic, then it's able to achieve success rate exactly same as GPT-4o, and the win rate is almost very close. It's not 50-50, but it's at least 48.2. So this is one step towards it. Again, if you see here, the reward functions are not well tied to the tool calling capability or things like that. This is more generic. You can apply for any trajectories that you have at hand. Now, like you might know that this is a setup where there is a single agent, right? There are also multi-agent systems where there is a master agent and a bunch of worker agents, or they may be collaborating with each other with different prompts and different states. Like when you transfer your control to a different agent, then it will start off from the state that it's currently in by taking information from what was past, and so the context becomes the environment becomes more and more complex. So there are works that have started to tackle that as well. If you have multi-agent systems and if you have trajectories, positive and negative trajectories, then how do we fine-tune a small language model which will get performance same as proprietary LLMs, right? So this is a very active area of research. There are a lot of startups that does exactly this. Even recently, OpenAI released something called Agent Kit, right? And what they say is that you build agents with OpenAI models, and you can log those in an observability. There's something called observability softwares, where basically they log all the interactions that happen between the LLM and the agent, and then they save them for easy access and easy summarization. So if you give me the observability traces and some additional information that I want, then I will fine tune a small LLM for you using RL. There are certain tasks where even GPT-4o is not able to do good, right? So 40% is not that great, right? Like imagine like if 40% is the success rate for single generation. Now if you we looked at something called pass hat k that measures reliability in tau bench, right? So if you do that and measure what is the likelihood k of my k times I do the same task and I get the right output, that will go down even considerably. So this success rate of 40 is not going to be something that you want to use at real life, right? So people are trying to bump this number up even for small language models. So what if you get from 40 to 80? Then is when is okay to use, right? But eventually you should get at something like 90, 95 for it to be actually used. So the only way people see it going forward is you have to do RL for your specific agent at hand, right? So there's a lot of work going on here. So if this is something that interests you and you like RL, then this is a good space to be in. Okay. All right. To summarize, we looked at two aspects of where agentic in agentic AI agents. One is memory management. We discussed a very basic paper. There are a lot more things that are going on now, and most of the memory management is mostly from the designer standpoint. It's more like system building rather than research at the moment, but that's very essential in building good AI agents. But the second thing we looked at is slightly more researchy, and this is an active area of research. There are a lot of papers coming in, and we discussed one good paper from called SweetRL. All right, thank you.